Let us start today's lecture with chalking out the differences between the three statistics, and then we will talk about the Bose-Einstein condensation mainly from the historical point of view and giving you some details, and then of course we will do an analysis of the Bose statistics and get into details of or derivations of the Bose-Einstein condensation, where we will be talking about the macroscopic buildup in the lowest energy state of the system. Okay. So, what are the main differences? This is just listing out them in the tabular format. So, in Maxwell-Boltzmann, which is abbreviated as MB, Bose-Einstein as BE, and Fermi-Dirac as FD. So, what is the particle nature in MB and BE and FD? So, in MB they are distinguishable, and in BE they are identical and indistinguishable, and in FD they are identical and indistinguishable. Of course, in BE also they are identical, but they are distinguishable. What are the experimental conditions that we get MB statistics? We get in low density of particles or high temperature or both. In BE we have high density of particles and low temperature, and similarly FD statistics would be valid for fermions at high density and low temperature. So, the quantum statistics become visible or rather perceptible at large density and low temperature. In the other limit, all these fermions and bosons, they act like classical particles. So, regarding the occupancy in a given energy level, there is no occupancy constraint in MB. It is just that the partition function is divided by n factorial, which we have seen elaborately. In B statistics, there is no occupancy constraint again in a given energy level, and in FD there is a strong occupancy constraint by the Pauli exclusion principle, which says that no two fermions should occupy the same energy state. What happens to their statistics? Now, what we mean by statistics is under the particle exchange what happens. In Maxwell-Boltzmann, of course, it gives rise to a distinct state, we have seen that, and in Bose-Einstein it does not give you a distinct state, and in fact under the exchange of two particles the wave function remains unaltered. This is called even exchange statistics. And what happens in Fermi-Dirac? It follows odd exchange, which means that if you interchange two particles or swap the positions of the two particles, then you pick up a minus sign, which is equivalent to a phase of pi. So, if you think in terms of phases, then the Bose-Einstein particles, or the particles which obey Bose-Einstein statistics, they do not pick up a phase, or the phase picked up by them is 0, whereas the phase picked up by the fermions, that is the ones that obey Fermi-Dirac statistics, that is equal to pi. With regard to spin, and of course classical particle has no concept of spin. Spin is a purely quantum mechanical quantity, and the Bose-Einstein statistics is valid for integer spin, and for the other one, that Fermi-Dirac, is for the fractional spin particles. So, I show you a video here and it tells you something. First see the video. So, there is a person who is holding the cup and is rotating the hand, is fully rotated the hand, and he has now rotated it twice and it comes back to the original point. Now, this tells you that the fermions actually behave like this, because under twice or rather a 4 pi exchange, that is if you exchange it or take it around the other. So, one particle is taken around the other, it picks up a minus sign, you take one more time, that is a rotation of 4 pi, it comes back to the same point. So, it is basically showing that. So, this the cup in the hand is like a fermion which is undergoing a full 2 pi rotation, does not come back to the point, it picks up a minus sign or a minus 1, and then now it picks up under another full rotation, it picks up this the sign 1. So, that means that if you do twice such exchanges, you pick up a plus sign, which is understandable. All right. So, what prompted Bose and Einstein to propose this statistics, what was not known at that time, I have sort of told you in a bit, but now let me tell you a little more about it. And everything started with the black body radiation, and people used to study this black body radiation in the initial days when quantum mechanics was developing. And it was known since centuries that something that is heated, a material is heated, particularly a metal, it radiates heat, and the color that it emits, or the electromagnetic radiation that it emits, depends on the temperature. So, for example, if you have seen heating elements of a stove or a heating coil, then it initially gets dark red, which becomes 550 degree centigrade or so. It becomes bright red at 700 degree centigrade, and then orange, yellow, and then finally white, which is really hot. Okay. So, the emission spectra, emission of the electromagnetic wave, that spectrum depends on the material as well. I mean, we are talking about, so if it is a nichrome wire or a copper wire and all that, they would depend. So, the electromagnetic spectrum will depend upon the wave as well, I mean the material as well. And this was noted by Max Planck, and he got a Nobel Prize in Physics for this in 1918. And in order to explain this, there was this Wien's displacement law that was proposed, which said that this lambda max that you see here, so actually the electromagnetic radiation that has a non-monotonicity. So, this is in the y axis you have this intensity, or in arbitrary units maybe, and this is the wavelength in the x axis, and you see that there are 4 blue curves. This one at 1800 Kelvin, which is the sharpest, and then 1500 Kelvin, 1200, 900, and so on. So, all these 4 temperatures, and you see that the lambda max is shifting towards slightly towards lower energies. Okay. So, Wien actually proposed that this lambda max, that is a maximum wavelength at which basically at which the intensity maximum occurs, that is the lambda max. So, for this particular thing, this is the lambda max, and so on. Okay. So, this lambda max for this temperature. So, lambda max into temperature is a constant, and this is called as the Wien's constant, and he this Wilhelm Wien, he got a Nobel Prize in 1911 in an effort to explain this black body radiation. Of course, that does not show the characteristic, but at least it predicts a value for this lambda max into the temperature in Kelvin. Okay. And then the visible light is just an information that they lie between, visible light actually lies between 4000 to 7000 or close to 8000 maybe. Ultraviolet is less than 4000 angstrom or 400 nanometer, and infrared is like greater than 700 or 800 nanometer. So, there is also another effort by Rayleigh and Jeans, and probably called as Rayleigh and Jeans formula, in which the intensity actually is shown as, so this by this formula and so on. So, that is a 1 by lambda to the power 4. So, that is again valid for this part of the spectrum, that is a larger wavelength of the spectrum, but it of course does not tell you that there is a going up and coming down. So, this non-monotonicity is not explained. So, this remained as one of the outstanding problems in the beginning of this 20th century, continued for a while. Okay. And these major flaw at this short wavelength is known as the ultraviolet catastrophe, and this had to be settled. Okay. And then came S.N. Bose. So, S.N. Bose here, the Indian physicist, and of course, who does not know about Einstein. And in 1924, Bose proposed these statistics, which is the average number of particles is equal to this 1 by exponential beta epsilon I minus mu and minus 1, and this has been shown earlier. and this when you plug it into the average energy. So, this is the mean number of particles or average number of particles, and so this is the distribution basically, and from there you can calculate the average energy, and then you can calculate the intensity of the radiation by multiplying that average energy with the speed of light, and this is what we will do when we do black body radiation. And this correctly reproduce the formula that was or rather this trend, a non-monotonic trend that you have just noticed in this slide here. Okay. So, just plotted for a single temperature, but it shows this non-monotonic. So, this behavior that it sort of goes up and then it comes down, that is explained very well. All right. So, these are Bose and Einstein, and this happened in 1924. This was Bose's discovery, and when it was consulted upon by Einstein, he saw the merit of this, and this immediately became a nice sort of proposal. And the proposal was not only to resolve the black body radiation, and which incorporates basically the photon statistics that we have seen earlier. It opened up possibilities for macroscopic accumulation of particles in one energy state, which is called as a Bose-Einstein condensation, and in short it is called as a BEC. Okay. And even though it was in 1924, it took nearly 71 years to get this thing realized in labs, and it was finally done. And why was there such a long wait? Because you need to go to very low temperature to see these atomic condensates forming, because they cannot form at large temperatures, and we will see that why they do not form at large temperature. And the reason is that accessing temperatures or rather the technology of reaching very low temperature, and really we are talking about micro to nano Kelvin. So, it is probably the coldest thing in the universe that one can even think of, and you have to prepare that in the lab. You have to have a low sort of 10 to the power 5, 10 to the power 6 number of atoms, and they would show this condensation phenomena. I will tell you what the condensation phenomena is, but just show this, showing it just in the their experimental data. You see the Cornell and Wyman have done it in 95, and just 4 months later Ketterle also did it with bosonic atoms like rubidium and other atoms. And what they see is that in the left picture you see that this one, if I see a yellow, no, there is a yellow. So, this is at T greater than Tc, and this is at T equal to Tc, and this is T less than Tc. So, what is Tc? Tc is the transition temperature or the critical temperature at which the Bose-Einstein condensation occurs. So, if the temperature is greater than that critical temperature, let us call it as Tc, then you do not see any condensation. Now, this is a slightly misleading picture. It might give you a feeling that you are seeing the buildup in real space. It is not. In fact, this is a buildup in the momentum space. So, there is a certain technology. If I get time, I will tell you more about that technology, and at least try to tell you in brief that what it is all about. This is called the time of flight measurement. So, once these BEC is formed, then you slowly release some trap. Trap is which helps you to achieve very low temperature, and once you release that trap, the atom starts flying away or flying apart, and you take the photographs in quick succession by a very high speed camera, and then Fourier transform it and put it in K space. So, these Fourier transform spectroscopy is what you see. So, there is likelihood of buildup of particle in the central region that you can see here, and at T equal to Tc, the K equal to 0 or the 0 energy states start getting macroscopically occupied, and at T less than Tc you see that the peak is sharper and more number of atoms are there in the K equal to, or rather almost all the atoms are there in the K equal to 0 or E equal to 0 state, and this is what has been seen by them as a proof of Bose-Einstein condensation. So, a given energy state accommodates all the particles, and why does it happen, how does it happen, under what conditions does it happen, what are the implications of such a build up, we will all see that. Okay. So, 1924 was the initial discovery, and 1995 was the getting these condensates in lab. Okay. So, this is the first time it was seen in Colorado at this Boulder and in USA. Okay. So, let me show another schematic video, and this is again from the internet. So, I will show you this video. It will show you that how the particles which are randomly moving around, holding their particle identity like classical particles, as you reduce the temperature, they lose their identity of particle and they kind of become like waves, and below a certain temperature or very close to zero temperature, they become like one giant wave, and that is the Bose-Einstein condensation. See this. So, that is your energy scale here. So, you see that there are these the temperature is measured in this along the thermometer, and these particles are moving around. Now, the temperature is falling, the particles are becoming slow, and they are gaining in terms of their spread over larger space, and the temperature is still lower, and they are moving slower and slower, and they are coalescing in some sense, and these coalesce will finally they become one giant matter wave, and that is what BEC is all about. It is just a cartoon of that, but it helps you to realize that as you lower the temperature, and if these particles are allowed to occupy the same quantum state or the energy state, they will occupy that, and that will lead to Bose-Einstein condensation. And this is known as this taken from this site, and I acknowledge them. I acknowledge this video and show it here. So, now we show this different cooling techniques. This is a laser cooling. So, laser is being targeted from all directions, all the 6 directions, and it is impinging on this blue colored, which is the atom which you are trying to cool, and this is another magnetic trap. You see that there are these magnets which are green in color, and then there are these inside that there is this atomic condensate which you are trying to condense, and these laser beams are being they are made to impinge on that. And finally, I will not go too much into details about the cooling techniques, and you actually do this, that what you do is that you as if you reduce the cup size. Cup means the cup of coffee that you have, and what we do is that we try to blow from the top, so that the more energetic molecules do not touch our lips, and so that we are saved from burning. So, what we do is that we throw away, or rather get rid of, the more energetic atoms, and this is done exactly by reducing the cup height. As you see that the cup is largest at the left extreme, and then it's growing in size, and only the atoms which have very low energy, which means very low temperature, because energy is equivalent to temperature, they only stay, and that will help you. This kind of traps will help you to get the atoms which are very cold, and so that the condensate can be achieved. So, basically what Bose might have realized is the following, that he understood that this statistics has got something to do with the condensation phenomena. You can take two say balls which are marked as A and B, and of course, they are identical, but just for our own convenience we have written them or marked them as A and B, and there are two boxes which are like the quantum states which the particles can occupy. So, for a Boltzmann particle, it is A1 B1, A2 B2, A1 B2, B2, A1 and B2 and A2 and B1, all 4 are distinct possibilities, which means that A1 B1 means both the balls are in box 1, A2 B2 both the balls are in box 2. First in A is in 1, B is in 2, A is in 2, B is in 1. Now, for Bose particles, we do not have this distinction, but we still write it. They both can be in box 1, they both can be in box 2, and one can be in 1, the other can be in 2, or vice versa, but they would give rise to same state. Okay. So, that tells you that these combinations are more, they are like 1/3 of these combinations. So, these are 2 combinations out of 3 whereas these 2 are 2 out of 4. So, if the particles are indistinguishable and you do not restrict the occupancy of particles in a given energy level, then they are more likely to be bunched together, and that is the essence of Bose-Einstein condensation. So, this shows that there is these 2 will get 2/3 weight as opposed to half, which is there in the classical particle. So, this is what I conjecture that Bose must have realized this, which lays the foundation of the Bose-Einstein condensation. Okay. So, we will do this calculation of the Bose-Einstein condensation. So, we start with really ideal Bose systems, ideal Bose gas. So, we have Bose particles, bosons, and they are not interacting with each other, they are free bosons, and we are talking about 3 dimensions, and these particles have non-relativistic dispersion, parabolic dispersion, which is E going as k square. Okay. Now, we need to understand that the classical limit, which tells you n lambda cube is much smaller than 1, is no longer valid, and in fact, we are explicitly saying this because we are going to talk about low temperature. From the preceding discussion, it must be clear that we are really interested in the quantum regime, and where this exotic phenomena or these novel phenomena would is like more likely to occur. So, that is where we are interested in. So, this is no longer valid. Okay. So, we do not still have a temperature to be large and density to be small. In fact, we are in the other limit. Okay. And where just to remind you that lambda is given by this which we might have written as lambda t, which means that this is the thermal de Broglie wavelength, and this is the expression for the thermal de Broglie wavelength. Okay. Now, we are coming to the other limit, that is n lambda cube is of the order of 1, and this of course is the extreme quantum limit, or we are going to the quantum limit. Which means that the temperature is low and the density of particles is high. And now, what happens is that let us try to do the analysis of such a system or classical Bose system in presence under this condition. Okay. So, the way we start is the following: we would express Zg, that is the canonical or grand canonical partition function rather, or log of Zg, okay, in terms of the equation of state. This is an important step. And what we do is that if you remember that log of Zg was nothing but minus phi over kT. This was written earlier, where phi is the grand potential. Okay. And this is almost similar in form to the canonical partition function, which is related to the Helmholtz free energy, okay, or that F. Now, it is the grand potential, and if you remember that we have said this earlier, that this grand potential or you can write it with a G here. So, this phi G is nothing but F TVn, that is the free energy, the Helmholtz free energy, and minus mu n. So, that tells us that this is equal to PV minus PV over KT. This has been written down earlier. That tells us that log of Zg is equal to PV over KT. Sorry, this is PV minus PV, and so this is PV over KT. And this is how we relate the equation of state to the partition function, grand canonical partition function, and in this particular case we have related it to the log of Zg. Okay. All right. So, this is the starting point and we will use this. So, we will write down a log of Zg is equal to PV over KT and equal to minus of I and log of 1 minus Zf, which is the fugacity, exponential minus beta epsilon I. So, this is the form for this partition function, log of the partition function. Let us call this as equation 1, and in addition to that we will also so Zf is nothing but exponential beta mu, and in addition to that we will write down a second equation as well for the total number of particles, which is equal to Ni sum over I, and that is equal to sum over I 1 divided by Zf inverse, which means exponential minus beta mu, and exponential minus beta epsilon I minus 1. So, this will call as equation 2, and these two are the starting point of our analysis of ideal Bose systems, and from here on we will show that if you have favorable condition, that is if you are at very low temperature, there could be a macroscopic buildup of particle in the lowest energy state, which is what this Cornell, Wyman and Ketterle have shown in their experiments with atomic condensates. So, now here I remind you one more thing, that is if you need to convert this sum into the integrals, we would need the density of states, and this density of states was derived earlier, that it basically just asks you a question that in K space, if you have a sphere of radius k and k plus dk, then how many states are there in this annular region, and these give you the density of states, and we would call it as gk dk, and this gk dk is easy to compute. You simply say that if you have this is if you walk a distance 2 pi over L in 1D, you get 1 k point, and if you walk a unit distance, you get L over 2 pi k point, and if you walk a distance dk, you get a L over 2 pi into dk k points. This have been done earlier, and we just simply take it to 3 dimension by doing a cube of that. This gives you a cube, and this now between k and k plus dk, that is the annular region between two spheres of radii k and k plus dk, we have a annular region which is 4 pi k squared dk, and then this has to be multiplied by 4 pi k squared dk. Okay. Now, you see you have a dk and you have a k square, the dk should not be written twice. So, it is 4 pi k squared dk. Now, k square is like energy, and dk will be again you use this relation. So, use E is equal to h cross square k square over 2 m. that is the parabolic dispersion, non-relativistic parabolic dispersion, and we are specifically talking about 3D. So, we have a d epsilon is equal to h cross square k by m dk, and this k is nothing but, so dk is equal to m by h cross square, and then k is nothing but root over 2 m e by h cross square. So, this will come out and we will have a h cross there. So, that is your k. So, k is equal to root over 2 m e by h cross square. So, this is inside the square root. So, this is like root over 2 m e and 1 by h cross. So, that is what we have written, root over 2 m e, and then of course, you have a dk, this is the dk, and then we put it back into this thing. So, your d epsilon will have now a root over epsilon coming from dk and an epsilon. Now, this dk will have a d epsilon of course, and then we have it. So, this, if we combine this and convert it into g epsilon d epsilon in order to get the number of states between epsilon and epsilon plus d epsilon by using this dispersion relation, what we land up with is that it is 2 pi v, and then of course, we have this h cube, and then we have this 2 m to the power 3 by 2 epsilon to the power half d epsilon, and so on. So, this is the density of states that we need to convert this integrals into sum. This has been done earlier. Please go through this once more, and you will be able to solve 1 and 2 by using this density of states. But this density of states, let me write it once again, because this is an important quantity here. So, this 2 pi v by h cube, 2 m to the power 3 by 2 epsilon to the power half d epsilon, and so on. Okay. So, you have a term which is k square, which is epsilon, and you have a dk which has an epsilon there. So, this is the dk will have an epsilon in the denominator, right, because this will be inverse of that, and that is how you have a epsilon to the power half. Okay. Because there will be 1 by root epsilon and epsilon coming from the k square. So, that will give you epsilon to the power half. Okay. All right. So, I have missed that earlier. So, please correct that. So, there is an inverse of that. So, you put both epsilon, I mean both k and dk there in this expression to you. So, you get g epsilon. But this tells you this is a little strange, or rather it sort of is misleading, because this assigns 0 weight to the epsilon equal to 0 state. Now, it could happen, and as it happens here, this is the most important state that we have, or rather we need. So, we cannot assign a 0 weight to that, because this should now be treated separately. Okay. If it is there, it should be treated separately, because this is the most important state under consideration for this problem at very low temperature and maybe at larger densities. Okay. So, we will write down this expressions for the pressure and the number of particles as P over kT, that V has been taken or cancelled with this other this V that you see in the density of states, and this is equal to minus 2 pi over h cube and 2 m to the power 3 by 2, and I convert it into the integral with this epsilon to the power half log of 1 minus ZF exponential minus beta epsilon d epsilon. See, when you convert it into an integral, then this I index should not be carried over, because I index really means that you are summing over some index. So, we use continuum notation for the epsilon. So, this is everything plus or rather plus means there is a contribution coming from the 0 energy, which is nothing but that is simply log of 1 minus ZF. Okay. So, that if you look at this, yeah, okay. So, in this expression, so if you really put epsilon equal to 0, you get a log 1 minus ZF, and that is the contribution for epsilon equal to 0. So, one term. Now, you may be wondering that we have still written 0 to infinity, even though we have separated out the contribution of epsilon equal to 0. See, this is a continuum integral, or rather it is an integral with some integrand, and this integral just goes from all energies just accepting that epsilon equal to 0 to infinity. So, whether you start from a very small number leaving out epsilon equal to 0, or in the integral form you write 0 to infinity, it really does not matter to the integral. Okay. But really the epsilon equal to 0 contribution to pressure is coming from here. Pressure means P by kT. So, we have there is no V here, and we have separated out this is for all contributions where epsilon not equal to 0 contribution. Okay. Let us call this as equation number 3 here, and let us call this as equation number 4, and let us write down the other equation as well, and let us write down the number equation, which is 2 pi by h cube 2 m to the power 3 by 2 0 to infinity. Once again that same approximation is done. It is epsilon to the power half, and there is a ZF inverse exponential beta epsilon minus 1, and plus the epsilon equal to 0 contribution. So, this is epsilon not equal to 0, and this is the epsilon equal to 0 contribution, which is simply ZF divided by 1 minus ZF. You can see that very easily if you go to this thing. So, I put epsilon equal to 0. So, it is a 1 by ZF inverse minus 1, and then that can be written in this form. Okay. So, that is ZF divided by 1 minus ZF. So, this is called as equation number 5. So, this is epsilon equal to 0. So, before we proceed, let us try to see that what are the implications of these two terms which are for epsilon equal to 0, whether they are significant or they are insignificant. If they are significant, why they are significant, and if they are insignificant, we will sort of have to ignore them or neglect them, which is perfectly fine. But there should be a strong rationale behind that, and that is what we wish to see. Okay. So, if you look at the second term of equation, we have called it as 5, I guess. Yeah, equation 5, the last equation, second term of equation 5. Okay. So, I single it out because this is important, and this term is nothing but 1 by V ZF divided by 1 minus ZF. Now, in the classical limit, this term is negligible, because this term has no meaning, because ZF is much smaller than 1, and this term is negligible. But in the quantum limit, that is when ZF becomes almost equal to 1, this term actually becomes very large because of the denominator blows up. So, this term we can call it as this term is 1 by V ZF divided by 1 minus ZF, and because we are writing the density of particles. So, this is clearly the density corresponding to epsilon equal to 0, that is the lowest energy state. So, let us call that as N0 by V, that is the number density for the lowest energy state of the system, and this is extremely large, In fact, this can be infinity, because this lowest energy state, bosons, any energy state rather, there is no occupancy constraint, but this lowest energy state certainly has no occupancy constraint in the limit ZF going to 0. Okay. So, this is definitely important. And should not be missed in some sense. Okay, so I do a box of this and something that here I also take a box of this, and then we should not miss it. Now, let us look at the second term of equation 4. What is the second term of 4? That is, there is a minus 1 over V log of 1 minus ZF. Okay. How do we write this term? Because we have we got in the quantum limit ZF 1 minus ZF, this is equal to N0, which is the occupancy of the lowest energy state, epsilon equal to 0 state. So, if you solve for ZF in terms of N0, then ZF comes out to be N0 divided by N0 plus 1. Okay. And if you really look at this N0, so N0 is nothing but exponential beta mu, that is the occupation, and exponential beta mu, and so on. So, or we can write it as 1 divided by exponential minus beta mu minus 1. So, that is your N0. So, 1 minus ZF is equal to 1 minus N0 divided by N0 plus 1. So, this is N0 plus 1, N0 plus 1 minus N0, which is equal to 1 over N0 plus 1. Okay. And this can be written as 1 over N0, because N0 is very large. So, 1 can be neglected. So, this term that you see minus 1 over V log of 1 minus ZF is nothing but this is equal to 1 over V log of N0. Okay. Now, this can be neglected because N0 may be very large number. First you are taking a log and then you are dividing it by V, the volume, and in the thermodynamic limit your volume is very large. So, this still can be neglected. So, in the pressure expression we may not take the second term, but in the number of particles expression we should definitely keep the second term, which is the most important. So, that tells us that we are having a sort of situation in which these two equations that we have, this term can be neglected. So, neglect this term, and this term is important and cannot be neglected. Okay. And we have these two equations as the guiding equations to get our Bose-Einstein condensation. Let me now try to solve these two integrals. The P has both of them have one integral each, and let us try to see this integral. And okay. So, this integral in equation, what is that equation? The equation 4 can be written as, so it is like your epsilon to the power half log of 1 minus ZF exponential minus beta epsilon d epsilon along with some factors. So, we convert that into some kind of an x to the power half 1 minus ZF e to the power minus x dx, just to sort of notational simplicity, and this is from 0 to infinity. So, we will do a integration by parts, where there is a rule called eyelet, which means that the log function, if it is there in the integrand, that should be taken as the first function for ease in the computation, and that so we do that. So, this becomes equal to 1 minus ZF e to the power minus x. So, here we write x equal to epsilon, just that, and then integral x to the power half dx from 0 to infinity, and we have a minus term, and then we also have because of this there will be another minus sign, and this will be like a ZF e to the power minus x divided by 1 minus ZF e to the power minus x, and we have x to the power 3 by 2 divided by 3 by 2, and so on, and then we do some simplification, and this is from 0 to infinity. Now, this term is equal to 2/3 x to the power 3 by 2 log of 1 minus ZF e to the power minus x, and the limits are 0 and infinity, and plus a 2/3 ZF 0 to infinity x to the power 3 by 2 e to the power minus x, and 1 minus ZF exponential minus x. Now, you see this term is 0 at both the ends, that is both the extremities. In the lower extremity you have to put x equal to 0. So, the integral will be 0 because of that, and in the other extremity you will put this x equal to infinity. So, this exponential minus infinity will go to 0. So, this will be a log 1 minus 1. So, that will become, that will again give you a 0, and well, I mean not so exponential minus infinity will go to 0, and it will be log 1, not 1 minus 1. So, this will be 0 in the upper limit, in the infinity limit, and this is equal to 0 in the x equal to 0 limit. So, this is x equal to infinity limit. Okay. So, this term is 0. So, we are left with only this term. Now, what have we achieved? If we look at this form and look at the form that we have obtained for this other term, which is epsilon to the power half, that is the energy or the occupancy, or rather the density of particles in all the energy states apart from the epsilon equal to 0 state. So, it takes a form of that kind, excepting that this power of the numerator of epsilon is not half, but it is 3 by 2. All the other things are same, and that tells us that we have this x to the power 3 by 2, and that tells us that this too can be written as in a similar form using what is called as a Bose-Einstein integral. I will give you a more sort of thorough treatment of that, but now I do not want to disturb the flow of this discussion, and let me see what we arrive at for the pressure term and as well as the number of particles term. So, if you use the other term, so this is, let us say, the one that we have to calculate. So, now we write down this the number equation as n minus n 0 divided by v, which is equal to 2 pi into 2 m k t divided by h cube, and 0 to infinity, and we have x to the power half dx divided by a ZF inverse e to the power x minus 1, that is the integral that we have. And if we introduce a Bose-Einstein integral of the form so this is the form of the Bose-Einstein integral. This z will be nothing but zf. This z is some arbitrary variable here. This is equal to 1 by gamma n 0 to infinity x to the power n minus 1 dx z to the power minus 1 e to the power x minus 1, and let us call that as what was the equation number that we were at? Well, we were at this equation 5, and then we have not defined a new equation. Let's let's define it as equation 6, and let's define this as equation 7. So, now we can write these both the expressions, that is the pressure expressions and the number of particle expression, as P by kT, and this is equal to 1 over lambda cube. Again, this thermal de Broglie wavelength comes up, and we have a g 5 by 2 ZF, where g is this Bose-Einstein integral. Let us call this as equation 8, and we have n minus n 0. So, we take into account this n 0 on the other side and write it n minus n 0, which becomes the occupancy of all the excited states put together. So, from the total number of particles, we take out the energy occupancy, or not energy, but the occupancy of the epsilon equal to 0 state, and this is equal to 1 over lambda cube g 3 by 2 ZF. You see, there is a factor half, and there is a one, let me use a pointer, there is a factor of half here, x to the power half, and there is a x n minus 1. And if you look at this other thing, which has x to the power 5 by 2, let me go to that. So, there is a factor which is 3 by 2 here. So, we have a factor that is 3 by 2 here, and then n minus 1. So, n will be 5 by 2 here, and here n will be equal to, in the top expression in equation 6, n will be equal to 3 by 2. So, these are the two equations. Let label them as 8 and 9, and these two are the parent equations that we are interested in, and these will sort of give us an idea about the Bose-Einstein condensation. Lambda, as usual, is h over root over 2 pi 2 m kT, 2 pi m kT. All right. So, we now want to sort of take this as the guiding equations and get expressions for pressure and the number of particles in the excited state. And if we do the expansion of this Gn ZF, that is a Bose-Einstein integral, this can be written in a closed form as L equal to 1 to infinity. We will give you more insights on this Bose-Einstein integral, and this is L to the power n. So, this for a given n, you have to sum over L, where L is in the denominator and n is there in the there is a ZF to the power L. Okay. So, this is like ZF plus a ZF square by 2 to the power n plus a ZF to the power cube by 3 to the power n, and so on and so forth. Okay. So, this is the Bose-Einstein integral, and we are interested in ZF to be close to 1, and that is the limit that we are interested in. So, this expansion till a finite number of terms is not valid, because this expansion comes for small ZF. Okay. So, we just simply cannot do an expansion and get some results. Had it been for ZF to be small, then keeping first and second order would be good enough, say first order would be good enough, and that is what would give us the classical limit, which we will see later. Now, n minus n 0, that is equal to the n exc, this means the excited state occupancy, and this is nothing but equal to V, and then you have a 2 pi m kT by h cube whole to the power 3 by 2 and a g 3 by 2 ZF. Okay. Now, this we are, of course, we know that, so we need mu to actually the occupation cannot be negative. So, we demand that zero is of course ZF less than equal to 1. So, we want mu to approach 0 from the negative side. Okay. So, that tells you that your G 3 by 2, which is there in this expression of in equation number 9. So, G 3 by 2 1 ZF equal to 1, this is equal to 1 plus 2 to the power 3 by 2 plus all that. This has a closed form, it is called as a Riemann zeta function 3 by 2 and has a value which is 2.612. Okay. Now, I am coming at is that if we look at this last equation, that is equation number 9, and evaluate this expression for ZF equal to 1, and that is what we are interested in, and there we get a value. So, there is a particular value of this form at a given temperature. Okay. And what it means is that if you have the number of atoms to be lesser than that, then of course, all the available energy states are occupied, because the excited states have some energy and the total number is less than that. So, all the particles are delocalized, and which will happen at temperature say greater than some critical temperature. Now, as you are at very low temperature, and you know that and there is a macroscopically large number of particles, that is, if your n is very large, much larger than your n excited, which means, so this is like a n excited state occupancies by V. So, your n excited is limited, okay, and which means that if you have very large number of particles, where would they go? They would go to the zero energy state, and this is called as a Bose-Einstein condensation. So, the very fact that there is a limited occupancy for all the excited states put together at very low temperature, the remaining particles or all the this very large number of particles will go to the lowest energy state, because the lowest energy state has infinite occupancy. This is what we have said, that this has infinite occupancy, because you see that it is here. So, this has infinite occupancy because ZF goes to 1 is this fraction diverges and n0 becomes extremely large, or it goes to infinity. So, when you have the ground state to have, or the lowest energy state to have infinite occupancy, so if you have more number of particles than what the excited states put together can hold, all the other particles will go to the ground state, and this is called as the Bose-Einstein condensation, and will of course happen at given temperature, and this is given by this. So, the n excited will have this V over lambda cube G to the power 3 by 2 1 means ZF equal to 1. So, this is the n excited max at T, at a given T, and this upper limit actually decreases with decreasing temperature, and the ground state, or there is macroscopic accumulation of particle at very low temperatures. And this is called as the Bose-Einstein condensation. Okay. So, this as I said that this maximum occupancy of the excited states will go down with temperature. So, as the total n is very large, all of them will have to go to the ground state, and there is a ground state accumulation. And this is what these picture that you have seen earlier here, that at t less than T c you have a macroscopic accumulation at k this epsilon equal to 0, which of course corresponds to k equal to 0, because E equal to k square or h cross square k square by 2m. And this was predicted by Bose-Einstein statistics, which was later experimentally observed in labs. Okay. We have many details to cover. We will stop here and we will carry on from next class onwards. And you have to remember that it is going to get mathematically a little challenging to get all the information regarding pressure or internal energy or various other things that are associated with it. How what is the contribution to pressure above Tc, below Tc, and various other things. And if it's a Bose-Einstein condensation is a transition, is a phase transition, is called as some new state of matter, then there must be a this transition temperature, and this transition temperature has to now it has to be decided that what is the order of transition and so on. So, there are many details that are associated with which we will do it in the next class. So, I will stop here, and thank you once again.